Let's do a share screen. Okay, can you see my screen? I think you do, right? Correct me if I'm wrong. Okay, so very briefly, in problem set number 4, so quick, I don't know, tutorial, or a mini tutorial or a micro tutorial. So in problem set number 4, which I have here, which I finished grading, in question number 5, it says that a particle is subject to a force that is constant in the particle's rest frame. Calculate the trajectory of the particle in Minkowski spacetime. Namely, calculate x mu of tau, where tau is the proper time. And I even give you a hint that you can work in one dimension. And many of you, I thought this is a pretty simple problem, which even really involves special relativity. There is no general relativity here. Basically, you have a particle, right? Think of, I don't know, a train or something, and there is a force. But what I'm saying is that the force is constant in the particle's rest frame. So of course, if it is constant in the particle's rest frame, that means that it cannot be constant in the laboratory frame, right? So the first thing to realize here is that the force, if you look at the lab frame, the force cannot be constant, but changing, right? And so what you really need to do is to do a transformation from the particle's rest frame to the lab frame, right? And so in the particle's rest frame, since I gave you a 3 force, then the 4 force would be a 0f in the particle's rest frame. And if you want to know the particle's force in the lab frame, then you simply do a Lorentz transformation. Right? This is a force in lab frame. And the Lorentz transformation, of course, depends on the particle's velocity, right? Lambda mu nu, right, is just gamma, gamma, beta, gamma, beta, gamma. Right? Gamma is the particle's Lorentz factor, beta is the particle's speed. Right? So you end up that the 4 force in the particles in the lab frame, F mu, right, it's just going to be gamma, beta, F, and then gamma F. Right? And then it's just a generalization of Newton's second law, right? E squared x mu over d tau squared is just F mu over m. Now, right, x or d over d tau of dx mu over d tau. So dx0 over d tau is just gamma. So d over d tau of gamma and u. Right? dx1 over d tau. It's all in 1d. It's just f over m times gamma beta gamma. Right. What did I do here? Now u is just gamma beta. So we can simply replace it with Cu. So we ended up with a couple of coupled equations, right? D over d tau of gamma u equal f over m u gamma. And what we're up to, of course, is a gamma of tau and u of tau. But that's straightforward because that's a coupled first order equation. So you know the answer should be gamma of tau is just A times E F over M tau. And then the minus B E minus F over M tau, and U of tau is just A times E F over M tau plus B E minus F over M tau. And then A and B you get from the initial conditions, basically. And of course, from the fact that that U squared is just gamma squared beta squared, and just gamma squared gamma squared. All right. Now, some of you did it properly. I hope you did it by yourself without any help of anything. Because this is exactly, it's a classical problem for special relativity, right? There's no general relativity here, really. So it's really just for, practicing your ability of doing transformations and, really understanding what happens here. So, I strongly urge you to make sure that you fully understand what's going on around here and how to do it. Right, there's no general relativity here, just special relativistic. All right, questions about that? I think it's really seeing the problem. I think some of you might have got confused when I said that the force is constant in the particle's rest frame. Maybe that was the confusing part. I don't know. All right. The rest, I didn't really have much to say about problem set number 4. I haven't yet had time to grade problem set number 5. I told you I had some problems. I'm supposed to have somebody to grade your homework, but apparently that somebody decided it's too hard for her. I don't know why. So it falls on me. It's not too bad because I know that many of you, I can see what you're doing, and I see that many of you, by the way, I can easily see who is working together, who is doing by yourself. Very easy to see. I'm not against working together. I am, remember, spend the time now working on the homework. This is essential. You will not have this time to start developing things in the exam. All right, you will get confused. So I'm actually quite happy when I see mistakes, and as you already seen, I don't take many points for mistakes. The important thing for me here, I'm not going to be that nice in the exam, right? But so don't count on that. The important thing for me is that you actually work, and if you find something difficult, then come and ask. Don't copy. Okay. All right. Any further things about that?
I have a question regarding the last homework, actually, but it's not only about the homework, it's a general question, because we have a trace-free part of the Riemann tensor, but how do you define a trace of, a 4 tensor?
How do I define a trace of a 4 tensor?
Yes.
Hold on. Where did it appear?
You need to take the free part of the Riemann tensor, it's the wild tensor.
Yeah.
The free trace, yeah, so. Like in the Riemann tensor, you can contract only 2 indices, so maybe it's straightforward, but in general, I don't know. Or maybe it's not defined.
Let me confuse for a second. Let me see. Where was that? For the Riemann tensor?
In question 2, you write the wild tensor can be considered as a trace-free part of the Riemann tensor.
Okay, let me answer this question later on because I cannot see it right away. Okay, so if I don't answer to you at the end of this lecture, just drop me a mail and I'll answer to you.
Okay, thanks.
In an ordered way, right? I don't want to just say something without being sure about it.
Okay.
Okay, so sorry for that. I will come back to that later. Okay, so recap on what we did. So last time we developed Einstein's field equation. And as I told you, this is basically the heart of general relativity, right? So Einstein's field equation. R mu nu minus 1/2 R G mu nu is 8 pi G T mu. This is an equation between tensors. On the left-hand side, we have the geometrical part, right? We have the Ricci tensor, the Ricci scalar, G mu nu. Essentially, this is the Einstein tensor, which we obtain by the Riemann tensor, which by itself is obtained by the metric, the inverse of the metric, the derivative of the metric, which is the affine connection, and the derivative of the affine connection. This is the geometrical part. On the right-hand side, we have the matter contacts, right? T mu nu. So the stress energy tensor, so matter or physical. This equation essentially tells us, given the distribution of material in the universe, or in space, general space, this will tell us how this material acts to curve the space-time, right? Now, what you see here really is, of course, 16 equations in four-dimensional space, right? Mu and nu can get any value from 0 to 3. And they are extremely difficult. It's a nonlinear. Nonlinearity means that if you happen to know a solution, two solutions, and any linear combination of these solutions is not by itself a solution, right? We have 16 equations, so not all independent, right? These matrices are symmetric, so that means that there are only 10 equations. But then in addition, we have the Bianchi identity, which gives us 4 constraints. So really, we have 6 independent equations. So 6 independent equations. Which we need to be able to solve simultaneously. Now, okay, so as I say, the importance, it expresses how the presence of energy or mass acts to curve space-time, describing how the presence of energy or mass acts to curve space-time. I say it's extremely difficult. The first solution was actually found quite shortly after Einstein wrote the equation. So the equation was written in the famous paper in 1915. Already a year later, Karl Schwarzschild found a solution known after him, the Schwarzschild solution. A few years later, there were other solutions which were found. The Robertson-Walker solution, the Nordstrom, I always forget the second name. Nordstrom, somebody else, which I forgot his name right now. Reitzner-Nordstrom solution, which generalizes the Schwarzschild solution to charge to electromagnetic fields. And then for many years, as far as I know, there were no new solutions until Roy Kerr came in the 1960s with his solution, which represents rotation of a black hole. Today, essentially, this is a generalization of the Schwarzschild solution. The Schwarzschild represents a non-rotating black hole. The best of our knowledge, there are no other solutions for black holes. But again, I have to be careful because we don't really know. There could be other solutions, but they were never found today. There are people that try to find solutions. Of course, the way it's being done is using computers, is using various methods. Perturbation methods are not really useful here for various reasons, which you can, I guess see. So it's them hard equation. People, there are people who spend their career trying to find new solutions to these equations. One thing which we also discussed is that you can add another constant to these equations. So you can put here another constant, lambda, which will depend on g mu nu. When you take the derivative, it will get to 0. So it's automatically conserved. When you put it on the left-hand side, this is called the cosmological constant. Einstein's original motivation to add that was his belief that the universe is steady. This was just a belief at that time. There was no evidence supporting that. After several years, Hubble discovered that the universe actually is not steady, but is expanding. And then Einstein, the legend says, I don't know if it's a true legend or not, but the legend says that Einstein called it the biggest blunder of his life, because hadn't he insisted on putting this constant there, which has no real physical meaning, and the value is just put in by hand. And, if you get a certain value, then you can get a universe that is not expanding. Hadn't he insisted on doing that, he would have predicted Hubble's law. Actually, I'm going to show you that towards the end of the course.
I have a book in Hebrew. It's a translation of Einstein, a popular summary of Einstein short after he wrote General Relativity.
Yeah.
And he addressed this mistake there.
Okay. Well,
maybe I can send you by mail.
Cannot be very shortly after, because Hubble made this discovery in 1927 or 29, I think.
Oh yeah, it has some.
More than 10 years after Einstein wrote down his equation. The textbooks of popular science and the history of physics are full with this thing. This is one of the most famous points in the history of science. So I wouldn't be surprised. Yeah, it's very nice. You can send it to me. You can send it to everybody.
But this is Einstein. Einstein wrote it. It's not on Einstein.
Yeah, Einstein realized that his mistake after he saw Hubble's results.
David, please send us all together.
Okay, I'll just. Okay, I'll send it.
Yeah, okay. It's a nice piece. Thank you for that. And then Einstein abandoned that for many years. And then it made a huge reappearance back in the 1999 with the discovery that the universe is not only expanding, but is also accelerating the expansion. Again, we will discuss that result down the line. And this is something which makes absolutely no sense when you think of it, because essentially what we have here, right? We have matter in the universe, and gravity attracts, right? We speak about that. The gravity does not repel. So you can imagine a situation where you have some sort of an initial condition which causes the universe to start expanding, but then the matter pulls it back. You cannot imagine a situation where there was some initial conditions causing the universe to start expanding, matter pulls it back, and then somehow, suddenly, it actually accelerates again to continue to expand further. So you can get that by putting some value here. The alternative is to take this and move it to the other side, and then it becomes some sort of unknown matter, and that's called the dark energy. So the dark energy is, again, I'm kind of going slightly beyond what I'm getting too forward, because we will discuss that thoroughly in several lectures time. The dark energy is some source of energy. It's a vacuum energy whose origin is unknown that causes the universe to expand. We still don't have a clue on what it is. Don't confuse that with the dark matter, which is a material which we can measure its gravitational attraction, but we cannot measure its light. That's why it's called dark. So it's two different things. Dark matter is matter which we do measure its gravitational attraction, but we would expect it to emit light the same way as if you look at the total mass of the solar system, right? 98% of the total mass of the solar system is inside the sun. The sun emits light. Here we have a situation where we have a large fraction of material which is not emitting any light, but we can still measure its existence using gravitational, this gravitational force. Dark energy is something else. Dark energy is what causes the universe to accelerate its expansion. Now, this is what I'm talking about here. It contains total of, it's not something which is negligible. Measurements show that it contains about 70% of the total available energy in the universe is within this dark energy. Another 25% is the dark matter, and only 5%, or about 4%, is the matter that we actually understand. So 96% of the total energy content that there is in the universe is something which we don't have any clue what it is. Even more interestingly, this within the framework of the best theory we have, a quantum field theory, we actually do expect to have some vacuum energy, because we treat vacuum like a collection of oscillators, and we saw in quantum mechanics that when oscillators are in the ground state, they still have an energy. So it's essentially, it's a quantum mechanical effect. So we have the same in vacuum. We assume in the framework of quantum field theory, a vacuum is simply the ground state of fields, which essentially, when they're excited, they produce particles. And we also have, but the problem is that we have a prediction of how much energy should be there. And the discrepancy between the theory and observations is 120 orders of magnitude.
שאלה בבקשה. מי יותר, התצפיות או התיאוריה? כשאתה אומר יש הפרש של 10 בחזקת 100.
התיאוריה.
התיאוריה יותר מהתצפיות.
כן.
תודה.
So something here is obviously right, obviously wrong. Something in the theory is obviously wrong. But any time that there is a discrepancy between observations and theory, the problem is always in the theory. Don't forget that for a second. Okay. So the only thing that it tells us is that there is something very deep in the physics that we do not understand. So there's plenty of room for you guys to get into this field and get these things straightened up and understand it. I can guarantee you a Nobel Prize for those of you who managed to solve that. All right. Now, the next big thing we're going to do is to try to solve Einstein's equation. But as I told you, we have a problem here, because trying to solve Einstein's equation is very, very difficult. So what we're trying to do, of course, in such cases, is to find some symmetry of the problem, because we use symmetries to reduce the complexity of the problem. But of course, the question we have, so idea, find symmetries of metric so that we can solve Einstein's equation. But of course, the problem is that we're trying to find symmetries of something which we don't know, right? We don't know the metric. If we knew the metric, we could say, we can look at the metric and say, okay, we find some symmetries. But we're trying to find the metric using symmetries which we don't know that they exist, right? So in other words, what we're trying to find is a general way of describing symmetries in what's called a covariant language, which means that they're going to be independent on the metric and independent on the certain coordinate system. So right now we're looking for some mathematical tool that would enable us to find symmetries in a covariant form. We look for a mathematical tool, to find covariance symmetries, namely in a coordinate independent way. And that leads us to the next topic, which is called the Killing vectors. Now, don't be afraid. Killing vectors is nothing too deadly about them. It's simply following the mathematician called Wilhelm Killing, a German mathematician. All right. Now, okay, what do we mean by a symmetry in general? So we say, consider that we have a manifold M, right? We say that it has a symmetry if we can make a certain transformation of the map M and the geometry will stay invariant, right? Which means that, in other words, that the metric is the same in two different points along M. So we say that a manifold M has a symmetry if the geometry is invariant. Under a certain transformation. That maps M onto itself. As usual, it's actually much easier to visualize than to do all the math. So, you know, the easiest thing I can think of, consider that the metric, which is like a bagel shape, right? So we have a symmetry, right? What do you mean we have a symmetry? We have a rotational symmetry, right? What do I mean that I have a rotational symmetry, right? I can rotate around this axis and there is a symmetry here, right? But what does it mean? I can take a point here, right? I have a g mu nu, so the coordinates would look something like that, that's fine. So if I go in this direction, there is no symmetry, right? The metric will look somewhat different. The space will look somewhat different. But if I go in this direction here, right, then the metric looks the same. The metric will not change. Right? So that's what I mean that I have a symmetry. Right? And the symmetry is related to a direction. Of course, a ball has symmetries in all directions. So it's a maximally symmetric space. Right? You with me? Now, such a symmetry, it has a name, this is called isometry. So a symmetry of the metric, symmetry of the metric is called isometry. So that's what we're looking for. We're looking for isometries. Now, the simple example, I'll give you another example towards the end, right? Look at the Minkowski space, right? Example. Right. Look at Minkowski space, ds squared, right? Eta mu x nu just minus 2t squared plus dx squared plus dy squared plus dz squared. Right. So there are several isometries of this space, right? So isometries would be, right, translations, right? So if I do a translation from one point to the other, right, x mu goes to x mu plus a mu, is some constant, the metric is not changed, right? I'm seeing the same space here and here, right? So Euclidean space from Minkowskian space. Can you give me other isometries that you know of in a Minkowski space? Is it only translations or there are other isometries that you can think of? Oh, come on, you're not with me.
And also have rotation.
Yes, exactly, right? Same for 2D space, right? If I'm standing here, right? Now I can go here. Space is empty, right? I'm looking around me, I'm seeing exactly the same thing. Right? This is an isometry. I don't care where I am, I'm seeing the same thing. The same if I have a rotation, right? I'm standing here, but now I rotate my coordinates. I'm still seeing the same thing, right? Doesn't matter how I defined, where I defined the north, you know, I don't know, I don't have a GPS or a compass, so I'm looking there. I'm in the middle of the sea, okay? I'm looking each direction, it looks the same. Okay? So that's an isometry. So another isometry, translation, another one is a rotation. Right. X mu goes to lambda mu mu x. Right. Now, if I look at the metric, there is a very simple way of recognizing that there is an isometry. What is that? If I look at translations, how do I know that the metric is invariant under translations? It's quite easy. Because I'm looking at the coefficient of the metrics, right? 1, 1, 1, 1, right? The coefficients of the metric, G mu nu. Oh, this is not G mu nu, this is eta mu nu. Right? And they're independent on the coordinates. Right? I don't have any dependence on the location, X, Y, or Z, or time. Right? So that automatically tells me that the metric is invariant under translations. It doesn't matter where along the X axis I am, because the metric doesn't depend on X, on the values of X. Right? Yeah? Or am I going slightly too fast? So we can recognize that the metric is invariant under translations. Since none of the metric coefficients at mu depends on the coordinate. Now, in some sense, this is an artifact, right? I could write down the metric in a spherical coordinates. I just chose the coordinates to be, Cartesian. I could have written them in spherical coordinates, then it would not be manifested so easily. Right? Because in spherical coordinates, the metric does depend on r and theta, not on phi. Right? So I wouldn't see that. I would say something else. I would say that it's a rotational symmetry. That's a different thing. Right? Another way of writing it is that if I'm taking the derivative of the metric with respect to some direction, which I specify by x sigma, so d sigma g mu nu equal to 0, right? For some direction d sigma, right? Then if then what happened? There is a symmetry under translation along x sigma. Right. If sigma g equal to 0, that means sigma goes to x sigma plus some constant a sigma is a symmetry. Yeah? Again, it's the mathematics can be slightly confusing, but it's really not that hard when you imagine it. Just try to imagine this thing here, right? When I'm moving from this point here to a point here, I just do a rotation and I don't see any difference. Then this is an isometry. If I'm going in this direction, this is not an isometry because now the metric does look different. Right? Okay. Now, the isometries are particularly useful. Questions? Questions? No. Again, those of you who do not open your cameras, please do so. It definitely makes things more lively. Okay, so the importance of isometries is associated with the motion of particles along geodesics. Let's see why. Isometries and motion of test particles. Along geodesics. And the reason is that the momentum component of the particle in the direction of the isometry, right? Isometry is at a given direction, as I just showed, right? Is conserved, right? The momentum component E sigma, E sigma of a particle is concerned. So the conserved quantity of the motion. Okay, proof. Right. Remember that the geodesic equation, right? You can think of it as some sort of version of Netto's theory. If I have a free space, right? I said I can move from here to here, right? In free space, and momentum will be conserved, right? Now the geodesic equation, right? We wrote it down as nabla u. It's just u lambda nabla lambda u mu is equal to 0. Right, u mu is just the x mu over tau for velocity. Okay. Remember we did that. So the shortest path is also the path which is when I'm parallel transporting a vector tangent to the path, it stays parallel to itself. Right. This is the geodesic. So, right. So this is so we can think of u mu as for velocity. We can multiply by m, so we have p mu. Just m u mu is for momentum. So we have p lambda 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 p q equal to 0. Momentum, so we just multiply m. And we have that. Now I can lower the index. I can simply write down, p mu is just g mu mu p mu, but then nabla nabla lambda g mu rho is equal to 0. This is the metric compatibility. So I can write it down. I can just use it to lower the index. So we have p lambda 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 p mu is equal to 0. And now I can expand that. Now we expand. So we have p lambda d lambda p mu, right? Minus gamma rho lambda mu p lambda p rho is equal to 0. That's just writing down the covariant derivative. Now, the first term here, this is the change of the momentum along the path, right? So p lambda d lambda p mu is just m dx lambda over d tau, right? D lambda p mu. So just m dp mu over d tau. So it's just a change of the momentum component along the path. Right? Now for the second term, for this one. We have gamma rho lambda mu p lambda p rho. Now I actually have to expand it, so it's half g rho mu, if I wrote d lambda g mu mu plus d mu g mu lambda minus d mu g lambda mu times p lambda p rho. So we can use the g to raise the index of the p rho. So this is 1/2 d lambda g mu mu plus d mu g mu lambda minus d mu g lambda mu times p lambda p mu. But now we have a symmetry between lambda and mu, so we can simply replace them because we're multiplying by p lambda and p mu. So that means that this term will cancel out with this term. Because if I change the lambda and mu, then those terms cancel. Okay. So we ended up with 1/2 d mu g mu lambda times p lambda p mu. So overall, we ended up that the geodesic equation is m dp mu over d tau is equal to 1/2 d mu g mu lambda p lambda p mu. So far, there's nothing that should worry you, and I didn't even make any use of the symmetry. I could have done that a few lectures ago, right? Right, there's nothing alarming here. Now comes the trick, right? Now we said, okay, if the metric is independent on the coordinate, right? So if the metric g mu nu is independent on the coordinate x sigma. So d sigma g mu nu is equal to 0. Then what do we get? So from the isometry, I mean, this is the isometry, right? And what do we get from the geodesic equation?
Zero, this is conserved because the derivative is 0.
Right? dp sigma over d tau is equal to 0. Right? If this is 0, then this is 0. So here I just proved to you. Right? Now, this result holds along any geodesic. Right? So along any geodesic, isometry implies conservation of momentum. So along any geodesic, isometry implies conservation of momentum. right? Now, if you notice, we did it for a time-like geodesic, but it's true for any geodesic. So, the fact that, these exist means that these isometries are extremely useful for us, right? Especially when we come to discuss the motion of test particles in curved spaces, that's going to be extremely useful to find these isometries. Make our life much easier in analyzing the motion of particles. All right, questions? No. Then let's discuss, killing vectors now. So the general discussion of symmetries and killing vectors. Still don't figure out how to have nice handwriting using this iPad. So potentially the problem is not in the iPad, it's my handwriting. But hopefully you manage to live with that. That's part of the reason I give you my lecture notes. So that, if you cannot read what I mean, but if you really don't understand what I'm writing, just stop me. So we said that if we see that the metric is independent on one of the components or coordinates, then we have a symmetry. But that's not the end of it, right? The opposite is not necessarily true. Right? We just show that if we look at Minkowski space, right, we have 4 translations and but also 6 Lorentz transformations. So overall, there are a total of 10 isometries, which is more than the dimension of space. The dimension of space is only 4, but there are actually 10 isometries. So we need to find a way, a general way of finding isometries, which is not necessarily depending on what we're seeing directly on the metric. Simply because the metric does not always tell us what are the isometries in a straightforward way. Okay, again, if we were to think of, to write down the Euclidean space in spherical coordinates rather than Cartesian coordinates, we wouldn't see immediately the translational invariant, although of course it's there. Yeah? Okay, so we want to do something which is systematic. So what do we do? Right. So let's assume, so we basically start from what we did here. So we want to find a systematic way of finding isometries. So we do the following. We start from this result, which represents the conservation of a component of the momentum, right? And we want to do it, we want to express it in a way which is independent on the coordinates. So dp sigma over the tau equal to 0 represents conservation of momentum component. We write it in the covariant form. Covariant form, namely independent on the coordinates, right? So let's assume that the metric is independent on some coordinate. Right? So assume G mu nu is independent on some coordinate which I call x sigma star. You see why I put the star there. So consider the vector which we call k. K, which is in the direction of sigma star. Sigma star basically, remember, vectors is defines passes on a manifold. Now, remember, any vector, we call any vector v, I can write as v mu d mu. So if I want to add in a component, I can just write down any vector. Right? So in components, what we have is k mu is just the sigma star mu, just delta mu sigma star. In words, so k, the components of k mu is 1 in the direction of sigma, and everything else is 0. Right? Remember, vectors are directional derivative. Right? So, yeah, we say that the vector k, we call it the generator of the isometry. So we say that k mu generates the isometry. Which means that, you know, if we take an infinitesimal change in the direction of k mu, the metric is going to stay invariant. Now, we can, using this vector, we can write down the components of the momentum in the x sigma direction. So the components of momentum in the x sigma direction. Right, in a covariant form. Now I can simply write it as P sigma star is just going to be K mu, P mu. K mu, P mu. Simply added up these delta functions. I have zeros everywhere. But now I wrote it in a covariant form, so I can change coordinates and it's not going to affect it. Okay. Now, this momentum is conserved along the path, right? So it is equivalent of stating that the directional derivative along a geodesic vanishes, right? So conservation of momentum is equivalent of stating that the directional derivative along the geodesic vanishes. Right? Because the covariant derivative along a path, right? B over d tau is just dx mu over d tau nabla mu. And P mu is just dx mu over d tau. So stating that dp sigma star over d tau is equal to 0 is equivalent of stating that P mu nabla mu and K mu P nu is equal to 0. Right, this is simply writing down the same conservation of momentum, but now in a covariant form by writing down P as K mu P mu and recalling that the covariant derivative along the path it's just d over the tau dx over the tau, so it's just P mu nabla mu, which is equal to 0. So now we can use this equation to write down to simply expand it. So we have P mu nabla mu K mu P mu. So now I'm actually going to expand it. It's just P mu K mu nabla mu P mu plus P mu nabla mu K mu. Right. Now the geodesic equation, right? P mu nabla mu P mu is equal to 0. Okay, make use of the assumption of the geodesic. That goes down. So P mu nabla mu K mu. But again, because of the symmetry between mu and nu, I can expand that to have a symmetric and an anti-symmetric part. And the anti-symmetric part is going to give me 0. So I can simply write it down as 1/2 P mu P nu nabla mu K mu plus nabla mu K mu. Right. That is because I used symmetry. So we ended up with an equation that needs to be satisfied by this vector K mu, which is that nabla mu K mu plus nabla mu K mu, which is just K mu plus K mu is equal to 0. And when this is satisfied, then this automatically implies that K mu P mu is conserved along the geodesic. And P mu nabla mu K mu P mu is equal to 0. Now this equation that I mark here, nope. This has a name, and that's called the killing equation. Now, any vector K mu, any vector K mu that satisfies this equation is called a killing vector. Now, of course, as we already demonstrated, if we have a metric and we write it in a form which is independent on some coordinate, then the, x sigma, then the vector d sigma is going to be a killing vector. But it's not necessarily the case. If a vector, the conversely is true, right? If a vector satisfies killing equation, then it is always possible to find a coordinate system in which the metric is independent on that vector, on that direction. Okay, so the killing equation is much more general because it is independent on the exact shape of the metric, the exact form of the metric, which is something which we arbitrarily chose. Right? Okay. The way you can see it is just go back to see how we derived it. We started from a general direction, which we did not specify what it is. We just show that every time in this direction, the momentum is conserved, then you end up with a vector that satisfies killing equation. Okay, so I should write it down. If a vector can satisfies killing equation, it is always possible. What happened? Find the coordinate system. Which caves D sigma. Right. The metric is independent on the coordinate x sigma. And if you want to prove that, just follow exactly, just reverse back what we just did. Okay, just as a remark about that, when the number of dimensions is greater than or equal to 2, there are already more killing vectors than dimensions. So just by looking at the metric will not give you all the possible set of killing vectors. Now, it may sound a little bit strange until you think of this Minkowski space, or even a two-dimensional space. Right? In two-dimensional space, you have rotation, and you have true translation, right? The way to think of it is that at any point on the manifold, the vectors would have to be dependent if you have more vectors than the dimensions of the space. But the vectors are defined throughout all space. So although at any one point they are dependent, they are independent when you're looking at the entire space. Okay. To practice that at home, I'm going to give you problem set dealing mainly with killing vectors today. So again, the coefficient of a linear combination of killing vectors, they can vary, they're not constant for the manifold. Questions? Okay, so what I'm going to do now, any questions? Okay, if you don't have any questions, what I'm going to do now, I'm going to give you another derivative This derivative of this scaling equation I took from the book by Carroll, and I have another derivative by the book by Weinberg, which does it in a slightly different way. I think in some sense it's a bit more straightforward, or maybe even more, I don't know, somewhat complementary, although I have to tell you that when I refreshed my mind this morning, I think that I'm not so sure that the derivatives are that different than each other. But anyway, I'll give you another derivative of the Killing equation, the second derivative. Of the Killing equation. It's going slightly deeper into some of the concepts that we have. So again, assume that we have some manifold M. We always start from some manifold. And now we put a vector field on the manifold. So one way to think of it, consider manifold M and a vector field. V mu. So, you know, you can think of a manifold, let's say, to be the sphere. And then the vector field, right, is defined everywhere in that space. There is a vector field. Right. On any point on the manifold. Now, this vector field defines an integral curve. So we define an integral curve, integral curves. The vector field. By by those curves that solve dx mu over dt is equal to v mu. Now, don't get to, it's pretty tricky. We already used that, but in the opposite direction, right? We said that when we have previously what we had was we had a curve on a manifold, and then we identified a vector as being tangent to the curve. Now we're kind of working the opposite way. We're given a vector and we're defining a curve on the manifold in the direction of this vector. Also kind of say a reverse to what we did. Now we can always do that as long as we have a nice manifold, no edges, no sharp spikes or anything. Anything, any well-behaved manifold, any physical manifold. Right. So the vector v mu defines a curve, which we specify by the parameter t. Now, we basically look at these curves as defining it what we call the diffeomorphism. So these curves define what's called the diffeomorphism. Now, I don't know if you remember, I gave you once a tutorial about the exact definition of manifolds, and it appeared there. Essentially, a diffeomorphism is a mapping between two manifolds. But what we have here is a mapping between the manifold and itself. So basically, we're taking a point here, and we map it into another point. So each point is mapped to a second point. Right? So that means a mapping phi between the manifold to itself. Right, that's a diffeomorphism. Right, so each point P on the manifold is mapped to another P on the same manifold. Right? Now, what we can do is to ask what happens to a tensor. How does a tensor changes if I have a tensor at P and I, let it travel down the manifold, down this integral curve. Now it's slightly different. There is a very subtle point here. It's different than what we did so far. Because what I'm doing is something, a bit different. It's a new way of defining mapping, basically. What I do is I take the tensor. So what happens to a tensor? As it travels the integral curve. I basically do two things, right? I take the tensor, I evaluate the tensor in the new point P prime. Right? And then I pull it back. I transform it back to the point P. Right? Another way of seeing that is that I'm basically transforming the coordinates such that in the new coordinate system, the point P prime will have the same value as the point P in the old coordinate system. And then I subtract the original tensor. Now, if I take all that and I divide it by t, the amount that I went over, then I get really a derivative. This is called a Lie derivative, in case you've heard of. I just described to you how you do a Lie derivative, which is a general derivative in the manifold. Now, again, so it's more difficult to understand than to imagine, I think. It's more difficult to explain than to imagine. Again, what I do, I'm going back to the example I gave here. I take the point here, I just move the tensor here, and I then rotate it back to the same point, and I see what happened to the tensor. Again, I took my tensor, which was defined here, I shift it here, and then I basically take all that, rotate it back to the same point, and then I see what happened to the tensor. Right? If nothing happened to the tensor, which is what I'm after, then I call this tensor form invariant. Okay, you're with me? I think it's more difficult to give the explanation than to see that. Right? You're just taking the tensor, you're moving it there, and then you're shifting everything backward to the same location, and you see if something changed. Right? If the tensor did not change. So T of x mu is T of x mu prime, we say it is called form invariant. Or simply invariant. Okay. And then we call this transformation a symmetry. Of course, we're not interested in any tensor, but we're interested in the metric tensor. So, the transformation of the metric tensor, If you got the idea, I mean, it's much easier to, for me, it's much easier to see that than to actually give the precise explanation, right? You're taking the tensor here, you evaluate it here, you take it backward, and you're saying if there is something happened to the tensor. If something happened, that's the lead derivative of the tensor. If nothing happened, then you say it's form invariant, which is what we care about, right? So if we look at the metric tensor, right, then G, the transformation of the metric tensor, G mu prime at point x prime is just dx alpha over dx mu prime, dx beta over dx mu prime, G alpha beta at the point x. Or the inverse would be that G alpha beta over G mu nu. G mu nu at the point x is just dx alpha prime over dx mu, dx beta prime over dx nu, G alpha prime beta prime of x prime. Now the assumption of form invariant, right? G mu nu is form invariant. That's the assumption. Right? That means that G alpha prime beta prime of x prime is just G alpha beta of x prime. So we have G mu nu of x is just dx alpha prime over dx mu, dx beta prime over dx nu, G alpha beta of x prime. Now, any transformation that fulfills that, we call this isometry. Any transformation fulfilling that is an isometry. Now, x prime is just translation, right? So you can write down that x mu prime is just x mu plus t v mu, right? V mu is what we're going to call a killing vector field. So the condition that it's a killing vector field, of course, t is a parameter along the curve, so we can take t to be much smaller than 1. So that enables us to do a Taylor expansion. So we have the G mu nu, right? Dx alpha prime over dx mu, but x alpha prime is just x alpha plus t v alpha. So I can write it down as delta alpha mu plus t dv alpha over dx mu, right? And the same for the second term. So delta beta nu plus t dv beta over dx mu. And for the third, we have G alpha beta at x prime is just G alpha beta plus dg alpha beta over dx, so kappa v kappa times t. Now we can G alpha beta times delta beta nu times delta alpha nu is just G nu. So we just keep on first order terms in T. We end up that the 0 is equal to dv alpha over dx mu G alpha nu. Should get from here, right? Plus dv beta over dx nu G mu beta plus dg mu over dx kappa v kappa plus of t squared, which we don't care. So now lowering down the indices by writing down v sigma is g mu sigma v mu, and taking the full derivative of differentiating v alpha g alpha nu, etc. Then we have here 0 is equal dv mu over dx mu plus dv mu over dx mu plus v kappa dg mu nu over dx kappa minus dg kappa mu over dx mu minus dg mu kappa over dx, which is just dv mu over dx mu plus dv mu over dx nu minus 2v kappa gamma kappa mu nu, which is just v mu nu plus v nu nu is equal to 0. This is the Killing equation. I think essentially the second derivative is very similar to the first one. Only I nearly introduced the derivative. Just have to think of it in terms of the concept of isometry. If you're taking the concept of diffeomorphism. If you're taking one point and you're basically shifting your entire space, and you end up getting the same result. Okay, the second equation is already derived. Just a quick example before we go home. Right. So Cartesian 3D space, Euclidean space. Part 3. So the metric would be ds squared is dx squared plus dy squared plus dz squared. Right? Independent on either x, y, and z. So we automatically get 3 Killing vectors. Right, which will be associated with the translations. Right? X mu will just be 1, 0, 0, y mu is just 0, 1, 0, and z mu is just 0, 0, 1. But I told you these are not the only ones, because we also have rotations. Right? But how do we see the rotations? So the easiest way is to write down the same space using spherical coordinates. So write write down metric using polar coordinates. ds squared is dr squared plus r squared d theta squared plus r squared sine squared theta phi squared. So which coordinate do we see that the metric is independent on?
Phi.
Phi, right? So the metric is independent on phi, right? G mu nu is independent on phi. Means that R, which is d phi, is a Killing vector. Now we can write it down back in Cartesian coordinates. R would just be written as minus y dx plus x dy. So the components of the Killing vector R mu would be minus y, x, and 0. Now, of course, the choice of, this is rotation around the z-axis, but this was arbitrary. You could have easily chosen rotation about the y or x-axis. And that would give us, just by symmetry, straightforward to show the other two Killing vectors. The s mu around the y, so it would be a z, 0 and minus x. And what I call t mu, which is just 0 minus 0. These are the 6 Killing vectors that this Euclidean space has. All right. I think we're over time. You'll practice that more at home. Any questions?
Yes, I will ask you at the end.
Okay. Okay, for the question that you asked me at the beginning of the lecture, I still didn't have time to think of it properly. I'll give it a few minutes thought and I'll give you a proper answer on Sunday in the next lecture, I promise.
Okay, thanks.
Any further questions? No, everything's fine. Okay, so I promise you we'll get another problem set today. And I can do the stop sharing and stop recording. So thank you very much. Have a quiet and